Hello, I'm Carol Hollingsworth, the JPS Vice President of Sales. I want to thank you for joining us today. I'm with Iggy Bragato, the JPS Senior Sales Engineer. Iggy will provide you with today's presentation. We really appreciate your being here. Today, Iggy will discuss the latest SNV-12 analog receiver voter IP backhaul network, the methodology of it. This webcast will help us understand the relationship of IP addresses and port values that allow proper transport of receiver and transmitter audio and time synchronization data between the modules within the SNV-12 chassis and the remote QMT IP backhaul modules that are located in the receiver and transmitter sites. The industry-leading SNV-12 signal and noise voter comparator is the most popular product that JPS currently manufactures. The markets using this product are very broad and the applications are endless. We've had previous webcasts on the SNV-12 voter where we discussed some of the markets and applications. At this time, we will focus on some of the specific technical aspects of this very special product. We truly appreciate your being with us today. Now let's get to the real reason you're here today. Let me introduce Iggy Bragato. Iggy?
Okay, great. Hey, thanks again, Carol. Welcome everybody to the JPS Interoperability Solutions Weekly Product Briefing webcast, and hopefully everybody's well. And as you know, Carol's located in Oklahoma. I'm here in California, and the factory's in Raleigh, obviously. And I'm Iggy Bragato, Senior Sales Engineer, and we also have with us, as you know, Carol Hollingsworth, our Vice President of Sales. And in this week's webcast, as Carol mentioned, we're going to discuss the IP addressing and port values solutions that we use with the SNV-12 analog receiver IP backhaul solution. This should give you a better idea and understanding of really the relationship of specific modules that work to mitigate the effects of voting over digital networks. And like many products developed in the 1990s that were really designed to improve land mobile radio communications, many did not have network capabilities. And that included the original JPS analog receiver voter, which some may not know was the SNV-4, which was first introduced in 1994. And in those early days, the SNV-4 had an RS-232 serial interface that allowed users to access controls using an attached computer. And to this day, the RS-232 serial interface is standard on every SNV-12 coming out of our factory. And this serial interface is really still widely used for maintenance, and in lots of cases serves as an interface for dispatch consoles. And in 1996, the ever popular SNV-12 was introduced. So in 2000, JPS began production of the NXU-2 network extension unit, and this marked the beginning of a long line of network-centric products. And now literally everything JPS produces has some sort of network functionality. The NXU was commonly used to link remote radio systems together to allow the sharing of voice communications over standard TCP/IP networks that implemented the JPS ROIP protocol. And not only was the NXU-2 JPS's first product with a network interface, it began really a very interesting and sometimes not so favorable relationship with the SNV-12 voter, particularly when smart customers and dealers attempted to use the NXU-2 and subsequently the NXU-2A to deliver audio from remote receiver sites over digital networks to the head-end voter, simply to substitute lease lines. And because network jitter and fidelity of the FM spectral noise obtained from the receiver, voting of remote receivers using NXU-2 modules was really never recommended. And in 2007, we began producing the next generation control processor module, the CPM3, which introduced an Ethernet interface to the voter, and that allowed for remote control and monitoring using a web browser. And it was a direct replacement of the first generation CPM1 control processor module, which did not have a network interface. And in 2018, we introduced the IP backhaul solution for the SNV-12 analog receiver voter. This new solution included a new digital site voter module called the SVM3, as well as the complementary IP backhaul modem called the QMT1 and the QMT-R. And those modules will be the subject of this week's webcast. And the reason the JPS developed the IP backhaul solution was to mitigate the effects of voting remote receiver sites over TCP/IP networks. And on the surface, this sounds like a great idea, except for a couple characteristics related to the network and the use of vocoders in the ROIP protocol. With respect to the network, the issues that would arrive would be network jitter, and really not the network latency. We can handle the latency with receive audio delay settings in the SVM1 and SVM2 site voter modules. But the unpredictable variation of latency, which we call jitter, can cause receive audio of multiple receive sites to deliver their audio to the voter at different times. And if the voter can't vote all unsquelched receiver sites simultaneously, you can experience some misvoting anomalies such as echo, or maybe missing the attack of the receiver audio. The other issue with voting over digital networks is the use of vocoders that are used to compress the audio for the interest of conserving network bandwidth. So vocoders inherently are not designed to conserve the noise personality of the audio. And as you know, noise is very important for the SNV-12 to make proper assessment of the receive audio quality. And so the suppression of noise over ROIP network links will falsify the portrayal of the receive audio being of high quality or low noise, when in fact the correlated audio, the human speech, may be poor in quality. So the introduction of the SVM3 digital site voter module and its complementary QMT1 and the QMT1B IP backhaul modems were first introduced in 2018, and we're not really going to dive too deep into that theory, but you can also check out some of our previous webcasts on our website for more information regarding IP backhaul. So the SVM3 digital site voter modules that reside in the SNV-12 chassis are able to support up to 3 QMT IP modems, as you can see in this illustration. So as an example, we can use an SNV-12 chassis that is supporting both analog and digital backhaul links from receiver sites. And so this is a great example of a hybrid backhaul system supporting both analog and digital links. And so if we add the CPM3 control processor module, which gives the chassis some intelligence, and if we connect the computer with a serial cable or choose to use a network, you can remotely control or monitor the voter. The CPM3 also has a synchronization function that we'll address in a moment. So we can also go ahead and add our SVM2 site voter modules, and these modules will interact with the remote receiver sites, shuttling receive transmit audio back and forth from the remote site and the head end voter. And so for our example, we'll just add 3 SVM2 analog site voter modules to support the single receiver transmitter sites using lease lines, radio tie lines, T1 microwave, or even RF links. This example chassis can be also populated with a couple SVM3 digital site voter modules, and the SNV-12 chassis will accept any combination of analog SVM2 or digital SVM3 site voter modules in literally any slot position. So in this example, we'll place SVM3 modules at the right of this chassis. You can populate this chassis from left to right, right to left. You can even skip slots, literally in any order. Either way, functionality-wise, the voter will still be just fine. And personally, I like to see chassis populated in this particular manner, as it's much more easy to add or remove modules as the radio topology changes. And remember, digital site voter modules can support 3 receiver sites. This means we can assign 3 remote QMT modules to each SVM3 module over the network. We can even create some really nice site density in a single chassis, considering 1 slot can now support 3 receiver sites. And the advantage of co-locating the QMT module with the receiver is that we can really directly capture the receive audio and assess the spectral FM noise content of that audio, and then embed that quality value information into the ROIP digital packets. Since audio quality is lossless, we can now add it to the header of the compressed receive audio in the form of data and form the ROIP packet and then deliver that packet in a digitized form to the parent SVM3 module within the chassis. So additionally, each ROIP packet is timestamped for clock information that is contained within each of the QMT modules. The CPM3 also has a duty of generating what we call the system time sync. And the time sync is generated every 30 seconds and delivered to each SVM2 and SVM3 module over the internal chassis bus. So the time sync effectively resets the internal clocks of each of the site voter modules. And additionally, each SVM3 digital site voter module then delivers the same, a common time sync to each of their associated QMT backhaul modems, also resetting those internal clocks. So the internal clocks are important as they're used to establish a common timestamp for each of the audio packets representing the audio from each of the remote receiver sites. This will help later in the process to synchronize and align the delivery time of the audio derived from each of the remote receivers, regardless of the delivery method, could be analog or digital. And this is based upon the timestamp of the ROIP data, and namely the first ROIP packet in the receive audio stream. So the first instance any SVM2 or SVM3 site is unsquelched, the initial audio ROIP data will be timestamped, and the CPM3 control processor module will monitor each of the unsquelched receive audio streams and will force all site voter module interfaces to begin buffering or storing receive audio. When the last receiver site delivers its audio with the timestamp, the captured spectral noise for all eligible site voter modules will also be compared. The data will be dumped from the audio buffers all at the same moment. And so this will simultaneously release the audio from buffers, effectively mitigating the effects of the network jitter on a periodic basis. All receive audio is then aligned, and this is all accomplished without GPS or external timing references. So for receive audio alignment and spectral noise capture to be accurate, the SVM3 within the SNV-12 chassis and the remote QMT modules at the right of this chassis example must interact over a TCP/IP network in a very timely manner. So I think we should kind of break down the process of voting over digital links by understanding the IP addressing and port value relationships which occur with the SVM3 in the chassis and the remote QMT module. So let's clean up the chassis and let's kind of concentrate on the digital site voter modules and the QMT modules at the right of the chassis. So let's add 3 QMT1B IP backhaul modems at the receiver sites. And remember, you do not necessarily need to deploy all 3 QMT modules. You may need to only support a single IP backhaul link. So in that case, you'll simply deploy a single QMT1B module. When we log into the single SVM3 site voter module with a browser, we can kind of understand and easily see the communication path between the single SVM3 site voter module and its 3 subordinate QMT IP backhaul modems by viewing the system module configuration webpage. And again, each SVM3 module in the chassis will require a unique IP address. And so this is important because the remote QMT modules need to know which SVM3 module to send the ROIP receive data to, which includes the timestamp and the audio quality information. Since the SVM3 needs to accept the receive ROIP data from 3 different QMT modems, we need to designate unique port values for the ROIP. And customizing the ROIP port values may be important for your network administrator, particularly if you are using a VLAN or doing VLAN port forwarding for an example. So what makes these ports unique is not only the port value, 1321, 1323, in this case 1325, but the IP address of the ROIP destination, which is the SVM3 IP address. With this in mind, so let's add another SVM3 module and 3 more QMT modems, and we can reuse the same ports. We can do this because the IP addresses of each SVM3 module is unique, and those unique SVM3 IP addresses will be important for the remote QMT modules, and we'll see that in a moment. And because we use the client-server association model, just like a lot of our other products, we can provision each QMT module to accurately direct its receive audio ROIP data to only one specific SVM3 module. And even with a chassis fully populated with SVM3 modules, each QMT1B modem knows explicitly to send its ROIP only to a specific SVM3 module using one specific port. So if we take a peek at the QMT module, there is a field where you could enter the IP address and ROIP port of the parent SVM3 module. So this is the web browser page would be viewed if I log into the QMT module. So with this connection model, the SVM3 in the chassis does not initiate the ROIP connection with the QMT module. Instead, it's the job of the remote QMT to find its parent SVM3, and that's the client-server association connection model that we use at JPS. So we don't do that with the IP address and port values of the SVM3 modules. So we do use the IP address and the port values of the SVM3 modules. So we'll repeat this process with the two remaining QMT modules, and noting that the IP address of the parent SVM3 module, which is 192.168.160.231, and then designate different ports for each QMT module. Again, those ROIP ports are specifically assigned to specific QMT1 modems. So in a nutshell, we can simply tell QMT modules where to send the ROIP data. So we can add a second SVM3 module in the chassis to support 3 more remote QMT modems. We can then reuse the port values, but since the IP addresses of the two SVM3 modules are different, all QMT modules will explicitly know which parent SVM3 to deliver their receive audio data. So the IP address of the SVM3, very important, but the QMT 1B, the modem, the remote modem, not so much. In fact, you can configure the remote QMT module in DHCP, which I really don't recommend, as you would probably like to provision a specific and known IP address for remote access for maintenance and troubleshooting purposes. So I stay away from DHCP if at all possible, but it's still possible to use DHCP at the remote QMT site. You may have noticed that there is another port value called the QMT ROIP port, and this is actually a network port where transmit receive ROIP data is transferred at the QMT side of the network. And we have assigned port values at both ends of the ROIP link just in case we need to apply, for instance, VLAN port forwarding rules or other rules that involve specific port values. This just adds a little bit more flexibility to the network topology. So the default QMT ROIP port setting is 1221. And some of you that are experienced with NXUs or DSP2 modules, you'll see that port commonly used, the 1221 port for ROIP. And in fact, if the network doesn't require port forwarding, and most don't, all QMT modules can use the same port value 1221. And 1221 can even, in this example, be used by other QMT modules in completely different SNV-12 voter chassis channels. All right, so one last piece of data that we need to discuss is the time sync and how it relates to all site voter modules, whether they're analog modules, SVM2s that reside in the chassis, and digital SVM3 modules that also reside in the chassis, as well as how the time sync relates to the remote QMT modems at the receiver sites. And as mentioned earlier, the CPM3, the control processor module, generates a periodic time sync command that effectively resets the internal clocks of the SVM2 and SVM3 site voter modules inside the chassis. So this time sync is then distributed over the internal backplane and occurs by default every 30 seconds. You can increase or decrease that value, but from our experiences, we see that 30 seconds is really a good compromise in terms of frequency. And as you already know, the SVM3 digital site voter module can support up to 3 QMT1 backhaul modems over the network. So the parent SVM3 will pass along the time sync to its subordinate QMT modules, again, effectively resetting their internal clocks every 30 seconds as well. If we log into the SVM3 module in the chassis, we would see the default time sync port value is 3000, and that's a factory default. Again, this port value can be changed to support network requirements. Again, for instance, VLAN port multiplexing or port forwarding. And if we take a look at the QMT backhaul modem at the remote site, we'll also see that the time sync port value is also 3000. And because the remote QMT is specifically paired with its SVM3 module because of the IP address relationship, we can effectively reuse the 3000 value for the time sync port value on each and every SVM3 and QMT module that's supported by the chassis. You can even reuse this value on all SNV-12 voter chassis in an entire system. And this is all possible because every module has a discrete IP address, right? So if we fully populate an SNV chassis with 12 digital site voter modules, SVM3s, and then deploy complementary QMT 1B modems, this single LMR channel will require 49 discrete IP addresses and a total of 169 ports, which includes the port 80 for remote browsing into each module, and then duplicate this for each LMR channel, and you can really easily see that you're going to encounter a serious amount of IP address and port values. And remember, many of these port values are being reused, which also helps with the organization of the network topology. So I recommend building a spreadsheet to keep your IP addresses and port values organized, but it's simple as long as you treat, and this is important, it's really simple as long as you treat each SVM3 module and its 3 subordinate QMT modules as a single piece or a single unit, and you can develop nice patterns of IP addresses and ports. So in the red, I've highlighted a single SVM3 associated with its 3 QMT modules. And this is an example of a spreadsheet that I use. And this example only has 3 SVM3 and 9 QMT modules, and naturally a single CPM3 control processor module. Lots of IP addresses and ports, but really this spreadsheet tells the story. And you can see that each module has a unique IP address, including the CPM3 control processor module, which I really haven't talked a lot about in terms of IP addresses. You can see the CPM3 module at the top of the spreadsheet. And because the CPM3 communicates with other modules in the chassis over the chassis backplane, there is really no association over the external network that is required. You can even disconnect the CPM3 module from the network and in a single voter chassis configuration, and the voter will still continue to operate flawlessly. So in our last webcast, we talked about multiple SNV-12 voter chassis with the proper CPM3 firmware, which is the 3.x version of the firmware. And this firmware is able to support up to 60 receiver sites in a combination of analog or digital links. And the incorporation of 3 SNV-12 chassis in a single channel will require the standard JPS voter chassis expansion cable set. But because of the very dynamic nature of the IP backhaul solution, in this case, all CPM3 modules in a single channel must be able to share data and control over the network. So in this case, the CPM3 modules must be connected to the network for inter-chassis communications and naturally for remote control and monitoring of voter chassis. So in a single chassis configuration, CPM3 should be connected to the network, but really does not dictate how the IP backhaul solution functions. You can even disconnect the CPM3 from the network, and in a single chassis solution, IP backhaul should still be functional. So you can also notice the reuse of port values that are shared between QMT modules. And again, the IP addresses really differentiates each of the paths. So with proper organization of the IP addresses and port values, the collaboration with your network administration really be painless. So I hope this demystifies the interaction between the SVM3 and the QMT modules over the network, and with little understanding of the path of the data over the network and a little bit of organization, the deployment IP backhaul really should be trouble-free. And you can see the same port values repeated over and over again. And when I introduced an SVM3 and a QMT modem into my own voter test bed a couple years ago, it was nearly plug and play, and all I needed to do was just modify a couple IP addresses to suit my network, and the modules linked, and I was able to pass audio from my receiver sites into the voter. And it's incredibly simple, but you need to stay organized, especially when dealing with larger systems. So I'd like to thank all of you for joining our webcast today, and if you need more information regarding the SNV-12 IP backhaul solution, or if you have any questions concerning the distribution of IP addresses and port values between the SVM3 and its subordinate QMT modules, you can always call us directly, or you can visit our website at interop.com. And Carol, you want to close with a few words?
Yeah, just again, we thank you very much for being with us today, and appreciate you very much for joining us, and we hope everyone stays safe out there.
Thanks, everybody.
Take care.